displayed, and most importantly, you can hear me. Okay. Does anyone want to offer as a volunteer for me to pull you, because our friend Soham is not around, so you can at least tell me if I detect, so I don't have to be interrupting myself. It's a bit boring for you guys also. Who wants to offer as a volunteer? I can pull you in to replace Soham. Well, I mean, Soham is unreplaceable. You know what I mean? Anyone? Okay, that's fine. No one else? I mean, if you are fine, if you are okay with me coming back and asking, that's okay. Because okay, so I hope you can see. Yeah. Okay. Yeah. So I'll keep asking. Yeah. Okay. So this session, as those of you who attended the last session, we worked with compactness, and I said we would, define paracompactness in this session. But in the end, I decided to not do it because it's really a technical thing that I think it's just a little bit of distraction for most of you, that we don't need it. In particular, paracompactness is a weaker notion than compactness. In other words, every compactness is much more restricted. It's much more stronger. In other words, compact spaces are also paracompact. And for our purposes, especially in Module 2, when we are dealing with Lie groups, we are mostly going to work with compact Lie groups. So these are automatically paracompact, so nothing to worry about. But however, those of you who want to, get into it, it's not really hard to define these things. It's just I have other challenges today for you that I would rather that you focus on that than on this, technical stuff about paracompactness. Okay. So what we will do instead, I will ask you to assume that from now on, the topological spaces are Hausdorff. You know what a Hausdorff space is. And the second condition I will assume is that it is second countable. Remember what second countability means. It means that the space has countable bases, okay? Set theory 101, countable means that you can put it in bijection with a subset, with the n, the natural numbers, or a subset of it, right? So these are the two conditions that we need. Yeah, these automatically, as for our purposes, this will mean paracompactness. These two will imply paracompactness for our the spaces that we are interested in. Okay, so the reason for all this mumbo jumbo stuff, or even paracompactness and these things, is these conditions, they guarantee us the metrizability of the space. In other words, with this, we can guarantee that we can find a metric. We can equip the space with the notion of a metric or distance. If you are coming from an applied topic like physics, okay? So from now on, assume all the space, the topological spaces that we deal with to satisfy this to be Hausdorff and second countable, okay? Let me just check the chat to make sure that I haven't dropped out. Okay. The house, okay, good. So Barry's saying all good. Yes, separate. Yeah, so the Hausdorff obviously satisfy the separability conditions. Yes. Okay. And here's a thing that I recommend for those of you who want to dive into this, thing about paracompactness. There is this thing that he proves some interesting theorem that a regular topological space, then if a space is regular, blah, 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 then it's paracompact if and only if, blah, blah, blah. All this stuff, you can read about this. But for the rest, don't worry about this, only for those who are super curious. And for those of you who want to go into this and you are having some difficulty with the study or whatever it means you decide to go and learn about paracompactness, if you are having issues or something, maybe I can give you my own definition or something, or maybe help clarify. Just ping me on Discord or something. Happy to do that. But for the rest, just focus on this. Just insert in your mind that the space is Hausdorff, second countable. That's it. That's all you need to know. Okay. Anything else is just unnecessary distraction. And another thing I want to comment is in this section, some of the key concepts are very intuitive. Things like charts, atlases, all these stuff. These are like intuitive stuff that as travelers and these things, you people, you drive around, you have your atlas of the world. You go around, you open the pages, in each chart, there's a specific region of the earth represented, blah blah blah. These are intuitive stuff. But the way you will see them in a formal way might be a little bit intimidating, but that's how formal mathematics is. There's nothing we can do about it. So that's why I think you should remember this very interesting quote, that the way things are, often very intuitive things are translated into a formal mathematical language might be completely different. And it's just the way things are. Don't feel frustrated. But yeah, I hope I'm still with you. I will ask again. Okay. See. Okay, good. Okay, so let's go to the first notion that we need. First of all, before I proceed, can you see this slide, right? Yeah, okay, good. So this is a very important piece. This is the first piece of the whole puzzle. So it's like we have a big piece of elephant in this case, like it's the manifold, and then we cut the thing. So now we are defining the pieces separately, then put them together. So this is one of the pieces, a chart. So in this case, an n-dimensional chart where n is a natural number. So you have to pick, if you want to construct a chart, you need to pick what dimension you want to construct the coordinate chart on. Okay, so giving a topological space X with a topology, your chosen topology T or tau, whatever this thing is called, an n-dimensional coordinate chart on X is a triple. Now, this is also another thing different that I'm doing here. Most textbooks, they put a chart as a pair, but we will converge to that in a minute. I think it's easier to view it as a triple than to start with anyway. Yeah, the verdict is out anyway. Just let's see a few slides. You'll probably agree with me. So a chart, an n-dimensional chart is a triple consisting of u hat, and phi that satisfy these three conditions. The first one is that u is a non-empty open subset of X. In other words, U is in the topology, in your chosen topology, and U is non-empty, okay? The second condition is that U hat is an open subset of Rn, okay, in respect to the standard topology, okay? So this is an open set, this is an open set. This one is in the topology of the manifolds, the topological space. And this one is on the topology of the topological Rn as a topological space in respect to the standard topology. Okay, and then the final condition is that phi is a map from U to U hat, and it's a homeomorphism. Okay, so homeomorphism is something that happens between topological spaces. So this is implying that we are, in our case, we are considering this U as a subspace of topological space, in the sense of being a subspace of X in respect to this topology. And the same with U hat in respect to Rn, the standard topology, okay? So this is in that sense that this is a homeomorphism, okay? So the open set U is called a coordinate domain of the chart. So this U is the coordinate domain. So this is the thing that the region in the topological space that you identify, and you want to chart it, okay? So I'm using this term wanting charting the thing just to bring some intuition in the colloquial sense. And the phi is the way that you chart that particular region that you identify, okay? I'll leave this for now. How would you call this U hat? But here's a pictorial. Here's a nice picture maybe not a little bit informal, because obviously you can't put this in this is a Rn, for any n, in higher dimension. You can't print them in a 2D sheet of paper. But anyway, if you are having difficulty with that, just imagine this is a plane. This is R2. So this is our space here, X. And we have identified an open set here, U. And then we have identified another open set, U. So maybe the best way to say it is that I have this region. I want to chart it. And then what I will do, I'll say, okay, yeah, let me look at Rn. Where do you want to chart it? Maybe I will say, okay, yeah, I want U hat, this region here, this part, okay? And then it's all a matter of constructing a homeomorphism that take you from here to here. Now, in principle, this homeomorphism doesn't need to exist. In that case, you cannot chart it, right? But in our purposes, I'm already giving any open set. We are able to identify an open region of Rn and a homeomorphism between them. That's what we want. And this is exactly what manifolds will give us. So I'm already giving you some sort of a head start for you to see where we, why manifolds are needed. So in principle, the thing, this X, cannot be charted. Not every open set in here you can find the thing, but yeah. So this is just a pictorial thing of the concept. Let me check the chat. Can you still see me? I mean, not see me. Find a homeomorphism that goes from the topological space X to Rn. Okay, obviously that's not useful to us. What we want to be able to do is, whenever we identify an open region of X, we are able to find a homeomorphism. Okay, so this is exactly what I was saying. It's going to lead us to manifolds, because manifolds have this property that you identify any open region. In this case, you will always find a homeomorphism to some other region, in Rn. Okay. So, and now here's a simple example. Let me just go back again, just to make sure. Can you see the slide? I hope I haven't disconnected. Yeah. Okay. So here's a very simple example of an n-dimensional chart. By considering X to be Rn itself, obviously equipped with the standard topology, and then you identify the U hat as being Rn too. Why not? Obviously with the standard topology also. Then the claim is that this, this is an n-dimensional chart where ID here is the identity map. Okay, the identity map, meaning that, it takes any point to itself, right? So this is a chart. I hope you can see this. This is the simplest example that you are able to see. Okay, so in the literature, this is known as the standard chart on Rn. Okay, and likewise, if you have an open subset of Rn, and let's say you have the open subset and make U hat equals U itself, then this is also, I claim that this is also an n-dimensional chart. In fact, in a few slides, you will see a generalization of this, that indeed, when you have an open set of a manifold, that can yield a manifold, an n-dimensional manifold of the parent, similar to the parent manifold. You'll see what I mean. Okay. I hope you're still with me. Okay, so as I was saying, I defined the concept of chart as a triple, whereas in the normal textbooks they define it as a pair. So this is where we are converging. Okay, so from now on, I will stop using the triple. Instead, we'll just use the pair U and phi. So we use the open set. We just notate, just acknowledge the open set in X in the topological space and the homeomorphism. We forget, well, not forget, but we don't write the region in Rn for now anyway. Okay. And another thing is that obviously because phi is a homeomorphism, then it means that phi hat is nothing more than the image of the entire open set U, right? So from that point of view, also it means that I will be writing just phi of U instead of U hat. Okay, and one thing that I would like to call your attention, especially if you pick up the textbooks, is very often instead of using phi to denote the homeomorphism, most authors, they use the notation X. This is very typical, especially for those books that are tailored to theoretical physics, especially general relativity, for instance. So just a note on there. Okay, I'm still with you, right? Yeah. Okay. Good. Okay. So far, so good. Finger crossed the network will behave. So here's a challenge for you. Okay. It's very important that you go through this. It's a very simple challenge, using examples that we are all aware of. So the first one is consider the circle, equipped with the subspace topology of the standard topology on R2. Now, if we have this open set, this U1 equals S1, except this point 0 minus 1. This is an open set. Remember, this is a Hausdorff space. So when you remove a point from it, you still get an open set, right? Okay, there are other ways of seeing this, but you need to see this is an open set, right? Okay, and now let's assume that U hat is the real line itself. It's R. Okay, so the claim is that for each point in U1, if we define the map from U1 to R, like this, phi 1 of P equals X over Y plus 1. The claim is that this is a one-dimensional chart on S1. Okay, so this means that this map is a homeomorphism. Okay, so you need to double check this. And here's another question. The same again. In this case, the same again in the sense, let's consider a circle again. Okay, but now we have another open set U2, which is S1 except the point 0, 1. In the first example, we remove the point 0 minus 1. Now we are removing the point 0, 1. Okay, and let's assume U hat is real 9 again. Okay, so the claim is that if we define the map phi 2 like this, this pair is also the question is whether this is a one-dimensional chart on S1. Well, all you have to check is whether this is a homeomorphism, right? And I have a similar challenge here for the sphere. we have U1, in this case, U1, let's make it the sphere minus this point 0, 0, minus 1. And let's say U hat is the entire plane R2, okay? So for each point, we define this map like this. The question is whether, well, not the question. So the claim is that this is a two-dimensional chart on the sphere, okay? And now another question. So you have to verify this. So this means that this is a homeomorphism. So if you remove this, the thing is, this is essentially saying that the plane is of, yeah. So here's a similar challenge. So I really encourage you to go through this. This is what enables you to solidify and build examples. Sorry for that. So let me check the chat just to make sure that I'm with you. I'm still with you, right? So the recommendation is that's one of the reasons that I split the definition. So you can actually, in each concept, you are able to practice. So my recommendation is, first of all, verify the stuff here, and then maybe construct other charts. Chart the circle with the other charts. Chart the sphere with other charts. And you will see in maybe consider other spaces to see if you can chart them. Okay, so that's the chart challenge. Now we'll go to the concept of a chart around a point. So far we are talking about the open sets as a whole, without highlighting particular points. Okay, so now let's assume that let's consider a topological space. A chart around a point in the space, a point P, is an n-dimensional chart such that P belongs to it. Okay, in other words, P is contained in the chart domain. Okay, so that's called a chart around the point P. So we say we charted the point P. We can chart the point. So phi of u is called the coordinate system, local coordinate system around P. Okay, so phi of u, remember u hat, which is in Rn, is called the local coordinate system around the point P. Now the question is, wouldn't it be nice to have a local coordinate system for every point P in X? So for every P, we should be, to find a chart, so on the entire space, as you can see, this is another hint to why, manifolds are nicer, because they are the ones, the topological spaces that enables us to do this. Okay. Let me just check the chat before I go to the next concept. I'm still with you. I'm sorry, I'm very repetitive today, but I hope it's for your benefit, so I don't have to blah, blah, blah too long. Yeah, okay, good. Okay, so that's it. So that's the chart around a point. So we have a chart, and then we have charts around points, around each point. If a point belongs to the domain of the chart, then that chart is said to be around that point. Okay. Another key definition is that given a chart around a point P, we say it's centered in P if the first condition is that the zero, the origin, has to be in the domain of phi of u, so in u hat. Okay, and the second condition is that phi of P has to be 0. Okay, if that happens, we say that a chart is centered in at point P. Okay, if it doesn't happen, then it's not, the chart is not centered at point P. Okay, and here's a very simple example for you to see this exactly. Is consider the standard chart Rn and the identity. The question is, where is P? Where is which point P in Rn that this chart is centered at? In other words, which point P satisfies this? It's the origin, right? Because this is the identity map. It means the origin, the origin in Rn is the only point that can satisfy this. So therefore, it coincides exactly with our intuition of So it's very important that you unpack this, that you understand what's going on in here. And here's a very simple example that enables you to see this, okay? Okay, so I hope I'm still with you. Yeah, before I move on to the key thing, okay, good. Now, here's the definition of a topological manifold. So a topological manifold is, or in this case, an n-dimensional manifold, is a topological space that has this property of every point in the space has an n-dimensional chart around it. In other words, for every p in X, at least one n-dimensional chart that contains P, okay? I mean, the chart domain that contains P, okay? So this means that for any point P in the space, we can find an open set containing P and a homeomorphism to Rn, okay? Here's a pictorial thing that I did for you. So you have U, so you have point P. It means we can find there's an open set, in this case U, and we can find an open region of Rn again. So, and then phi of P obviously is mapped into this point, and this is a homeomorphism. Yeah. So manifolds are exactly what we want. It means that any point, essentially any point we can give. This is essentially the intuition is that every point in a manifold, every point can be charted. So we can give coordinates to any point on the thing in the space. This is very useful, especially for physicists, if they want to model, a particle moving in, whatever dimension and these things. If they use a manifold, it means they can give coordinates to the thing, to every point in the thing, in the whatever they call it, is a configuration space or something. The physicists in their lingo. Okay. So this is exactly where you hear when you hear that a manifold locally looks like Rn is because of this, because at every point, at very small neighborhoods, is homeomorphic to Rn. So locally, a manifold looks like Rn. So this is where the actual source of the joke that we will be telling here is that the flat Earth theorist might have a valid point, that the surface of the Earth is flat, but locally, yeah, not at the global level. Okay, so that's where they got it wrong. They should have maybe consulted a topologist before they formulated their theory. Okay, so I hope there is no. Can you still hear me? Yeah. Okay. So I hope there is no confusion here. Is there any confusion around? Does anyone have anything? Or is so far? I hope the way I broke it down, hopefully it didn't backfire. Frankly, I think by splitting this into different things and then putting them together is probably much easier to digest, because you can go back and refer back to the key concept that you are having trouble with. Say, for example, if you are having trouble with what's a chart, you go back there, Okay, so it seems that no one has any doubts. This is great. Okay. So here's a property. We will come up with more property as we go along, but one of them is this. As I was saying before, in the case of Rn, when I gave an example, there's a general thing of this. So if you have a topological manifold, n-dimensional topological manifold, and if U is an open subset of X, then as a subset, as a subspace of X, U is also an n-dimensional manifold. I hope you can, verify this. It's not that hard, but it's not that easy anyway. But yeah, this one is a little bit more harder to see. That's why I'm writing it here. I don't require you to think. Is that if N and M are different, then a manifold cannot be both n-dimensional and m-dimensional manifolds. In other words, the dimension of a manifold is invariant. You cannot have one manifold which is you cannot have a topological space that is a 4-dimensional manifold at the same time is a 5-dimensional manifold. Okay, so this means that the notion of dimension for manifold is well defined, is a well-defined notion. Okay. Another thing I want to comment is in textbooks, when n equals 2, you normally call the manifold as a topological surface, for instance. Okay. And also the term n manifold is often used instead of n-dimensional manifold, because obviously this is very wordy. So when you see like n manifold, like 2 manifold, 1 manifold, 3 manifold, 4 manifold, all it means is n-dimensional manifold. Okay. And finally, one convention that I will do from now on, so far, in this crash course, I've been writing this pair to denote the topological space, meaning the set together with the topology. But I will stop doing this and just use the x, denote x. And, at the background, you always should just know that there is a topology. There is an underlying chosen topology in there. And the space has to be, remember, Hausdorff and second countable. Okay. So from now on, I will stop the thing. I will stop using this notations. Starting next session, I will just write let x. In this case, let x be a manifold. For instance, we'll forget the the topology. It's there behind scenes, but we'll stop referencing it. Okay. Now, I hope you could see the previous slide. I'm still with you, right? The previous slide, this slide was, could you see this? There was no problem with it? Right, okay, good. So we are coming to an end, so hopefully the network stays stable. So here's a challenge. This is a very simple challenge, I hope, is which of the following are manifolds, okay? So, well, I mean, these guys are probably like, this is like obvious, but you need to prove it anyway. That's the challenge. These ones might be a little bit more trickier, but hopefully this helps you, solidify the stuff that we went through. So, if any of them is a manifold, then in principle, if you pick any point on them, you should be able to find an open set containing a chart around that point. You should be, in other words, you should be able to find an open set U, and you should be able to find a homeomorphism from that open set U to Rn. Okay, so I'll leave this as a challenge, but please go through this and go through the challenges of the chart and start. That's one of the reasons I split the definitions into smaller chunks. Define the chart first and so on. So you can actually practice building charts and these things, because in practice, when you are doing, computation and these things, you have to do it. Obviously, nowadays you have software and these things that does that for you. But yeah, nevertheless, it's very good to do, to have like a hands-on experience doing this by yourself, manual. It's a bit tedious, but it helps. Okay. Yeah, similarity with the previous challenge. Yes, this is partly because I was a bit lazy to come up with the new thing, but also in order for you to be able to build the connections, to not make it hard for you to see. That's the purpose.